Okay, so yeah, it's a pleasure for me to be here. And yeah, also today I will tell you a bit about our experience with DFT+U on ferroic materials. Oops. I'll be here. It's okay. I can stay here. Questo. Okay. So yeah, let me tell you first what I am, although Andrea already said. So I work in Chieti, and I lead a small group. And so our experience is more on, so-called correlated material oxides and organics. And recently we moved to the magnets, which is the topic of my talk today. So I'm a density functional theorist, as most of you are. So we benefit a lot in the ferroic community also from symmetry analysis and occasionally model Hamiltonian that helps us understand, what we see from DFT. Okay. So let's move on.
Questa è la luce.
That's okay. With the
No, it works.
Okay. Okay. Yeah. Okay. So, so when I received the invitation, I was thinking about what to, show to you. And so, because I mean, I don't develop methods, right? So I mostly apply methods to magnetic system, basically. And so I thought I would show some experience and some performances of DFT+U on a number of cases, going from successes, but also showing failures. So I have a kind of working knowledge on DFT+U, although we don't, the thing I want to say is that usually we don't evaluate the U from ESPRESSO. So what we do is like a poor women approximation. So we scan, some U values and check, whether the properties we're interested in change or not. Okay, so let me first remind what a ferroic material is, what ferroic material are. And so first, let me tell you that among the ferroic material, we have ferroelectric materials. So ferroelectric material are material that have a spontaneous polarization developing below an ordering temperature, so-called Curie temperature. And similar to the magnets, they are switchable, but not upon the presence of a magnetic field, but with the presence of an electric field. And so you have hysteresis cycle, you have Curie temperature, so they look very similar to ferromagnets, but their order parameter is polarization and variance with magnetization. So what ferroic material generally means is magnets, ferroelectric, and ferroelastic. So those materials showing a spontaneous deformation below a certain ordering temperature. And usually they are controlled by the conjugate field. So you control magnetization with the magnetic field, polarization with the electric field, and so with deformation you control the stress state. If you have a multiferroic, so a material which shows that more than one of these material, sometimes there is also a cross-coupling. So you can actually control polarization with a magnetic field or magnetization with an electric field. So they are so-called multifunctional material. So I'm mostly interested in the connection between ferroelectricity and magnetism. So in addition to standard magnetism, where you have your MH phase diagram, or PE for ferroelectric material, in magnetoelectric, which are often connected to multiferroics. You can also have an hysteresis cycle which is in the pH space or ME space. Okay, and so from the symmetry point of view, in magnets you break time reversal symmetry and you keep special inversion symmetry. In a ferroelectric you do the opposite. You keep time reversal symmetry, you break inversion symmetry with in a polar fashion. And in a multiferroid, you break both, right? You have your long range magnetic border, so you break time reversal symmetry, and you have a polarization, so you break spatial inversion symmetry. Okay, so having said this and having said the language, let's say, as I said, I scan the U. And so we look at our properties and then we publish the paper. And the most common question that we get is, I mean, how did the authors estimate the U? Did the result change? And so I will try to show you some interesting results where the physics doesn't really depend on the value of U, but also I wanted to be as fair as possible, and I will also show you the dramatic failures that you can encounter in your many systems. Okay, so let me first start with a lucky case. Physics doesn't depend on you. So what I'm discussing is some 2D material, basically. This is just an introductory slide. You probably all know. Started the whole boom started from graphene, and then with many 2D material, they are flexible and they're miniaturized devices based on 2D material. You can stack them the way you want. You can play Lego and many nice feature. After the boom on graphene, there came the boom on 2D magnets, which actually started with the finding basically of ferromagnetic behavior, basically starting in chromium I3 and chromium germanium telluride, 2016 and 2017. So basically, the 2D magnets are a rich playground for material scientists because they are chemically rich. So there are many, elements that you can play with. You have binaries and ternaries. They are electrically rich. Some of them are resonating, some of them are metallic, some of them are semiconducting. They are structurally rich. Some of them have triangular lattice, honeycomb lattice, orthorhombic. So they are, from the structural point of view, kind of curious. And of course, they are interesting from the magnetism point of view. You can have them collinear, non-collinear, ferromagnets, anti-ferromagnets, with easy access in the plane, out of the plane. So they are kind of, they show some variety that, of course, it's interesting to look at. So I cannot give a talk on 2D magnetism without mentioning the Mermin-Wagner theorem. You know that basically Mermin-Wagner theorem states that you cannot have any long-range order if your spin behave in an isotropic way. So whenever you have your Heisenberg Hamiltonian, this would never order in dimension lower than 3. So we don't expect any order actually in a 2D magnet. You need basically to break this isotropy in the spin behavior. And so typically in a real material, you actually always break it because spin orbit coupling, which is the interaction that links orbital and spin momentum, actually gives rise to anisotropy. For example, makes the spin pointing out of the 2D magnet or in the so sort of anisotropic effects are kind of always, I would say, well, shape also can, of course, make the system anisotropic, but from the electronic structure point of view, spin-orbit coupling is the source of anisotropy. Okay, so let me focus on this class of material, nickel halides. So I take like basically a monolayer of nickel chloride, bromide, and iodide. So they are, nickel is at the center of an octahedral cage. You compress a bit your octahedron, like in a trigonal, small trigonal compression. And if you look at the electronic filling, nickel is the 8th. It's octahedral coordination. So you basically have the crystal field splitting, T2G and EG. T2G is basically fully filled, and EG is half filled. So you basically get 2 Bohr magnetons. The important thing also when you compare chloride, bromide, and iodine is that you move down in the periodic table. So you expect spin orbit coupling to increase from chloride to bromide to iodide. Sorry. So these materials are interesting because they were characterized already back in the 80s in the crystal form. And they showed some complex magnetism. Some kind of spiral helix, which are some kind of exotic. And so we were wondering if this complex magnetism exists still at the monolayer stage. So we basically tackled the calculation of a monolayer of nickel chloride, bromide, and iodide. A couple of concepts that I need to show you the results. First thing is frustration. Frustrated person is what? Is a person that cannot satisfy all his or her need. So frustrated material is also material in which the exchange interaction cannot be satisfied at the same time. So typical example of exchange frustration is an antiferromagnetic coupling on a triangular spin. So if you have your antiferromagnetic couple on triangle and you arrange the 2 spins, then the 3rd spin doesn't exactly know what to do. If it lines up, then this interaction is not happy. If it lies down, then this interaction is not happy. So in the end, the system tries to find a compromise by counting in a non-collinear way. So typical, this is for 120 spin configuration, which tries to satisfy and make the system as happy as possible. So exchange frustration is strongly connected to the crystal. So you can have frustration in certain kind of lattices, triangular lattices, Kagome in 3-dimensional pyrochlore. And so in our case, we have triangular lattice. So we are sort of satisfying the basic ingredient of having exchange frustration. You can have also exchange frustration in a single chain, the simplest magnetic system that you can think of. If you have a spin of chain of spin, and you have your first exchange interaction, which is small. It can be ferro or anti-ferro, but needs to be small. And if you have your second nearest neighbor, which is large and anti-ferromagnetic, then 2 things can happen. If you have strong anisotropy, the spin orbit is strong and tries to align your spin along a certain direction, then the ground state is a spin chain, which is like up, up, down, down. So at least the second nearest neighbor interaction is always satisfied. If your anisotropy is not that large, then you have a helix or a spin spiral, not a helix, not necessarily helix. But I have something that where my spin have a non-collinear fashion. So these kind of exchange frustration, we thought that could be at the basis of the finding in the 80s of this non-collinearity in the bulk. And we were wondering whether exchange frustration are still there in the monolayer limit. So by DFT, you can basically estimate this exchange interaction by mapping total energy for different spin configuration, for the moment at the Heisenberg level. And so what you get by DFT is that your first neighbor is strongly ferromagnetic. Second nearest neighbor is basically 0. And then the third neighbor is strong and anti-ferromagnetic. So when you try to place your spin on your lattice, you start from, let's say, central spin. Then you, okay, first neighbor is strong and ferromagnetic. I put them up. Then third neighbor, already I don't know what to do, right? I would like to put them down because J3 is strongly anti-ferromagnetic, but then this interaction would be frustrated. And so I expect some non-collinearity from the exchange frustration. Okay, so this was already some hint, and here I did, this is a day on DFT+U. Here I need a U, because if I don't include a U, I get a metal. And so if I get a metal, then my exchange interaction are much broader than they should be, and the description is wrong. I will show you then in the end how wrong and how good. But for the moment, let's focus on the physics. Okay, so first, so far I use only Heisenberg. This one. So I have a J, I have a scalar term, and this basically describes the interaction between a spin SI, localized spin, localized limit, SI and SJ. And this is what we learn, right, in the magnetism courses. But actually, it is not completely correct. So one should describe the interaction between spin side I and spin side J through a matrix. So 3 by 3 matrix. I can always mathematically decompose a 3 by 3 matrix in 3 terms, a trace like an isotropic one, and then I can decompose the rest in an anti-symmetric part and an symmetric part from the mathematical point of view. From the physical point of view, what these 3 terms correspond to is this isotropic is the Heisenberg, the one we usually estimate. But then there are 2 terms, so-called Cieloszewski-Moria and anisotropic exchange, which can be described in this way. So one is a cross product. I believe I have another slide. Yeah, okay. Let me also tell you what these 3 terms tend to do. So, okay, this Heisenberg one, what does it do? It tells if my system wants to have parallel spin or anti-parallel spin. But it's isotropic. It means if they lie like this, or they lie like this, or they lie like this, it's always the same. This second term, Cieloszewski-Moria, what does it do? It's a cross product. So it's 0 if they are parallel, and so it tends to count the spin. But it's a chiral, it's a cross product, right? So it has a sign. So if whether they count like this or they count like this, it's different. This anisotropic term, which is usually neglected. I've been working on magnetism for many years and never calculated this term. It's usually believed to be small. From what it tends to do is also it tries to align the spin in a certain direction, but it's a 2-side. So it's not single ion anisotropy as we usually have. It's a 2-side term. So it tends to lie to make the spin align along a certain direction. And so also because it's anisotropic, they both anisotropic exchange and Cieloszewski-Moria are rooted in spin-orbit coupling. And so if you neglect in your calculation spin-orbit coupling, then you cannot estimate this term. If you do include them, of course you can. And so these were known actually since Moria back in the 60s. It's well known, but people usually neglect that, and usually they are small, right? But not so small that we cannot completely neglect them. Yeah, so this is called exchange. Symmetric exchange is actually often called 2-side anisotropy. So because it tends to align the spin along a certain direction. So in our case, we have inversion symmetry. And it can be shown that actually if you have inversion symmetry in your system, the Cieloszewski-Moria term is 0. So we don't expect any DM in our system. And then also by symmetry, because of the space group of the nickel I2 or nickel chloride 2, then your allowed term your allowed matrix has a certain form, which has basically 0 here, 0 here, and then in principle 3 different diagonal terms, and it's symmetric, right? Because dm is 0, so I need only to have this same JYZ is equal to JZY. But you see, I mean, I don't have a number which describes my interaction. I have a matrix. And this matrix I can estimate from DFT. I mean, I can, this was proposed not by our group. But I mean, you can estimate and you can use, I mean, this is a bit technical. I mean, you can do it with the so-called 4-state method, which requires a superset. I don't think that matters, but you can estimate. Of course, it's including spin-orbit coupling, is kind of delicate calculation, but it can be done. And so this we did. And so what you get? So for nickel chloride, this is the matrix you get. Basically, you have 3 diagonal terms, which by symmetry can be different, but they are not. So the Heisenberg description is perfectly valid for nickel chloride too. Heisenberg would say that basically all diagonal are 0 and all terms are the same. So nickel chloride 2 is a Heisenberg-like system. Spin orbit increases, and so as I move to nickel bromide, I start seeing diagonal terms which are a bit different, and also the emergence of off-diagonal terms. If I move to nickel iodide, the situation becomes much, let's say, more different compared to a standard Heisenberg term. So you see that I have, on the diagonal, I have the exchange coupling constant, which are very different, and on the diagonal, which are very large. So the ratio, let's say, between off diagonal and diagonal is like 15%. It's very large. And so this you understand, because all these dm and dm is 0. I mean, all these off diagonal terms arise from spin-orbit coupling. So it's reasonable that I get some large number on nickel I2 and 0, or close to 0 on nickel chloride. So now, why is all this interesting? So typically we have a DFT, it's rough, it's spin orbit, non-collinear, it's difficult. So we generally use an Hamiltonian, and then we exchange parameter evaluated from DFT, and then use Monte Carlo to get the so-called spin texture, so to get the ground state spin configuration. And this is what we did, just also to move to, I mean, to phase diagram and get the ordering temperature. Just a word on the notation. So I have in principle spin are 3-dimensional. So the way I will plot them is that I plot with arrows the projection on the plane, and with colors I plot the out of plane component. So this, let's say, vortex would be actually plot like this, with the color is out of plane or in plane, and then the arrows label the in-plane projection. So given that I evaluated all my exchange tensor, what do I get? So for nickel bromide, I get, well, that is so evident, but basically I get a spin helix. So a spin helix is what I have a wave, basically. So I have a propagation vector like this. And then my spin rotate in a plane which is perpendicular to the propagation vector. So this would be the propagation vector, and then I have spin rotating this. So it's kind of non-collinear, of course, complex, exotic. And if I evaluate the Curie temperature, ordering temperature, I get something small, around 20 Kelvin. This is what you expect. I mean, a frustrated system never has very large ordering temperature because it's frustrated. So the system doesn't exactly know what to do. So it can order, but it usually happens at low temperature. This we expect, right? Because I mean, we know that even from a simple model, we have a spiral or helix. What we didn't expect was what we found for nickel iodide. Nickel iodide, we have a much larger off diagonal term, and this is what we get, which we couldn't interpret in the beginning. What you can recognize is that you have a lattice So maybe you have a lattice, crystal lattice underlying, but you also have a spin lattice, right? You see some kind of periodicity here. And so we thought that it could be related to the so-called skyrmion-like particles. So what is a magnetic skyrmion? So we went back to study this skyrmion object. So skyrmion is what? Is a spin texture, non-collinear, non-coplanar, usually, actually non-coplanar, which has a topological origin, right? So there is topological charge, which I will come into in a moment. So there is a zoo of skyrmion. So usually typical skyrmion is like this. So you have a core spin at the center, and then the spin can rotate in a clockwise or counterclockwise, and they reach the border where you have a ferromagnetic bath. But you can have many complex patterns. You can have anti-skyrmion. An anti-skyrmion is, for example, you have your core spin here, and then they spiral clockwise in a direction and in a counterclockwise in another direction. So, for example, here you have clockwise like this and counterclockwise like this. So it changes the rotation sense as you change direction. And also you can, the way you understand the topological charge is by mapping your two-dimensional spin texture around the sphere, and how many times your spin texture wraps the center gives you the topological charge in a, let's say, naive or intuitive way. From the mathematical point of view, you can estimate this topological charge even in a discrete description of spin. And so by doing here, so you basically do a sort of spin chirality. So you take a triangle and you make the scalar product of one spin times the cross product of two other. So from here, you basically see that you need non-coplanarity. It's not enough to have non-collinearity, but you need to have non-coplanarity, otherwise this will be zero. So you expect some non-coplanarity. Okay, phase diagram of skyrmion system all look pretty similar. So typically you have something which starts from a helix, something very frustrated, and then you apply magnetic field and a skyrmionic region develops. But usually this is driven by Ceaușescu-Moria, and there's no Ceaușescu-Moria in our system. So we were wondering where this skyrmion or anti-skyrmion actually arise from. And so first we didn't know what they were, then we thought they could be skyrmion, and so we evaluated the Q, the topological charge, and we got actually that Q is 2. So it's an anti-skyrmion and it's a higher order. So usually skyrmion is Q minus 1. Here we have, let's say, positive, and then we have an higher order. So it wraps around twice around the sphere. Also, I mean, you can evaluate again the temperature by seeing, for example, when this topological charge, which can be taken as a sort of order parameter, emerges, let's say. So again, it's small, you expect it, it's frustrated, it's very frustrated. This is very frustrated, even more than the helix. And it's not driven by Ceaușescu-Moria. So the origin of this is unconventional. And so we thought, why do we have a skyrmion? And so we thought that maybe this anisotropic exchange has a role. And so, I mean, you have a symmetric matrix, right? You can always diagonalize it, and you can calculate your eigenvalues and eigenvectors. And so if you now map or plot your eigenvectors on the space, on the crystal space, you can refer, for example, to a plaquette. A plaquette is a system composed by, let's say, nickel iodine. So you have a sort of square here, and then you can plot your 3 eigenvectors. And if you do that, you discover that basically they align along the nickel iodine, and then the perpendicular one. And so you basically discover that the lowest, the strongest eigenvalues is the one that tends to align the spin perpendicular to the plaquette. And the plaquettes are non-collinear. And so just for this term, you would get some non-collinearity. So we believe that actually part of the complexity of the spin texture that we see is actually rooted in this anisotropic exchange. Okay. Yeah. So, question: does it depend on you? Because I told you that we don't evaluate. And so we were wondering if the exchange parameter and also anisotropic single ion anisotropy, which is this term, depends on U. And it actually does. It actually, if you change the U, the J themselves change. However, what actually gives the spin texture is the competition between these terms, the ratio. You can think of it as a ratio between different terms. And so if you do the ratio between, let's say, the off diagonal to a sort of average trace, or if you, for example, do the ratio between the third nearest neighbor with respect to first nearest neighbor, you basically see that they all look the same, depending on whether you use 1, 2, 3, or you use Liechtenstein or Dudarev. So your physics, let's say, your complex spin texture is safe, let's say, in this case, right? Doesn't depend so much on you. I mean, maybe the Curie temperature would, the J would, but the ratio, so the spin texture, the ground spin texture, ground state spin texture doesn't. So good news. Another lucky case is that if you have a good friend at the synchrotron that can measure something for you. And so in this respect, I will tell you about a system which is not rigorously a 2D magnet. So you have a 2D layer. So this is manganese 3, silicon 2, tellurium 6. So you have a layer which is like similar to one of the 2D magnet, non-2D magnet, which is chromium, germanium, tellurium. But then in between the layer, you have another atom. So you have a quasi 2D system. And so this is kind of intriguing material. It was shown to have a colossal angular magnetoresistance. So magnetoresistance is typically when you have strong change in resistance if you change the magnetic properties. Here, you have an angular magnetoresistance, which is attributed to the fact that you have a completely different resistance whether your spin align along, let's say, the z-axis or in the plane. This is a ferrimagnet, which means that you have ferromagnetic in one plane, and then you're in the plane, to say in between the planes, you have spin pointing in the opposite direction. Again, how to choose the U? You have your good friend that measure resonant photoemission that can basically tell us the partial density of states. So normal resonant photoemission is what I'll try to explain, although I'm not expert, of course. So you have your photon comes in, electron comes out. In resonant photoemission, you basically have a combined process. So you now have a photon which excites basically a core electron up to above the Fermi level, let's say the EG, but not out. And then you have an Auger decay, right? So this hole is basically filled by this electron here, and this energy is taken by this electron to go out. So the final state between direct photoemission and this combined process is actually the same. However, you have here, let's say, a completely different process. And so basically with this resonant photoemission, you basically map the partial density of states of manganese if you appropriately tune your photon energy to the threshold that excites from the core level to the shell. Right, so this is what they get. This is the experimental spectrum. And the remaining part of the resonance minus of resonance is presumably attributed to everything else that does not manganese, so presumably tellurium. And so what we can do is to scan the U and see where the peak matches. And so in this case, you see that something between, let's say, 1 and 2 would probably match the experimental spectrum. Now, what can happen, of course, is that sometimes a U matches your spectral properties, but then your description of, let's say, for example, magnetic properties is not accurate. Right? You need a U to fit the spectrum and another U to fit the J. And so we thought, okay, then let's evaluate the J with something like U equal 1 or 2 and see what we get. And we did that with the tensor. The exchange is again evaluated in a tensor way. And so you see that basically, something, the Curie temperature is something around, I don't know, 100 or something. And experimentally is like 80. It's good. We can never expect, to Monte Carlo and DFT to reproduce exactly the ordering temperature. So we are kind of satisfied here, even here, with the help of experimentalists. Quickly, the description which gives right trend, but of course, not quantitative description. Manganites are really terrible systems where many degrees of freedom are all active at the same way. Spin and charge and orbital degrees of freedom are active. Here you have many distortion. So you have rare earth here can have different ionic radius. And so depending on the ionic radius, you have tilting of octahedron. So you have first distortion given by tilting. Then manganese, here oxygen is 2-, the rare earth is usually 3+. Manganese is D4, so you have a Young-Teller ion, and Young-Teller gives a distortion. So you have an orbital order, which is a stagger orbital order, and your EG becomes split and occupied on let's say, X square and Y square arranged in a plane. And so you have Young-Teller distortion, spin ordering, tilting, so it's kind of complex system. And depending on the kind of tilting which you can reach by changing the ionic radius, so by changing the rare earth, you can get a very complex phase diagram. So as your rare earth ionic radius becomes smaller, your octahedra tilt more, and your exchange becomes more frustrated, more, let's say, helix and spirals. And so in this region, you actually have antiferrotic. So again, if I do use a U or not, what happens? What happens? So here I'm plotting the distortion. So Young-Teller, long bond length, short bond length, and also medium one, the one perpendicular to the plane. And what you see is basically that, I don't know, I mean, it's difficult to compare. But you can, in principle, say that for undistorted manganese, so here, maybe you need a +U. But then maybe for distorted manganese, if you add a U, there is a big deviation. So you're never sure exactly whether you should use a U. For the angle, you basically get similar trend. So I would say the conclusion is that you get a right trend, but quantitatively is not okay, neither U or without U. So when you have a complex system, where this is the message I'm slowly trying to convey, that the more your system is, the more complex is your system is, the harder it is to get a quantitative description, even with the U. And then final one, I believe it was, there was a couple of questions on the J. So I want to show a system in which basically we don't have any predictive power. Okay, so there was a question, I believe, on the J dependence. So usually people use Dudarev, rotational invariant, just results depends on U minus J. However, what happens if you have a non-collinear spin texture? Then you have to use a Liechtenstein approach. So here is Liechtenstein approach, as it was mentioned by Matteo and Yuri. So the problem is that if you have a non-collinear system, then you not only have your density, right, with m plus mz and minus mz, but you also have off-diagonal term. And so with off-diagonal term, you can sort of make an extension. I believe it was proposed by Eric Bousquet and Nicholas Holding, because you basically need to find an expression to add to this off-diagonal term. And so the expression they propose is this one. And you can see that basically it depends on J. So when at variance with the case of collinear spin, up or down, where basically your result depends only on U minus J, for no collinear system where your off-diagonal term are important, your result depends on J strongly. And I will show you that the dependence is strong. So this is not my result. This is from Eric and Nicholas Spalding. They were tackling systems which were shown in the beginning by Matteo, but they tackled lithium-nickel phosphide. So this has C-type spin configuration. C-type means you have spin aligned along the C-axis in a ferromagnetic chain, which is antiferromagnetically coupled to the neighboring spin. But then also you have a canting along A. So you have CZAX. So they count like this. So it's non-collinear. And the results basically that they were showing is that, for example, if you compare, let's say, U5 and J1 and effective 4, which in Dudarev would be same, actually you get two completely different results. When you plot, for example, the energy versus the counting angle. Counting angle means by how much the spin comes from the C-axis. So it's kind of important to include the J and to include in principle the right one. What is even more serious is that, for example, if you try to evaluate the magnetocrystalline anisotropy, so you basically evaluate your total energy as a function of the spin direction, then you go, for example, from an easy plane to an easy axis behavior, as you J. So the bottom line is that here you get a qualitatively wrong, I mean, strong dependence qualitative on the J. So, well, an evaluation of the J would be certainly welcome in this case, because this would give a way to estimate actually, basic properties. So I guess I can skip the last two slides. I think there is a, let me skip it. Let me just get to the take-home message. Of course, I mean, when you scan the U and you don't estimate, your predictive power is in principle zero, right? You don't have any predictive power, although in some cases, as I showed you in the beginning, your physics doesn't change. So you can always say, well, even if I don't have any experimental result to compare with, I can still, look at my property, and if my property doesn't depend on you, then I'm still safe. But of course, in general, the predictive power is not there. Well, this has been said, the second point has been said several times, it's not an atomic property, it strongly depends on the environment. So if I look at manganese metal, I have a certain U. If I look at manganese oxide, I have another. If I look at manganese iodide, I have another one. So calculation needs to be done on a case-by-case basis. Yeah, there is I mean, in principle, I mean, this also has been mentioned previously. I mean, DFT+U corrects self-interaction, but there can be a variety of errors that we can make And so the comparison between our result and the experimental result might be due to many other reasons, right? So Hubbard just corrects part of it, not all the error. The other message is that if you're trying to evaluate small properties, like a fraction of millielectron magnetic anisotropy, NDM, and anisotropic exchange, it's a challenge anyway. It's a challenge for DFT+U because these are tiny and be predictive is really hard. This also has been said. So sometimes, you know, your properties depends on DFT+U plus J plus V plus dynamic. And so the description of this system where you have many degrees of freedom that are all active at the same time is never easy. However, word of optimism is that sometimes trends are okay. So DFT, I mean, yeah, often, not always, but trends are, I mean, chemical or structural or magnetic are usually okay. And so with this, I would like to thank you and hope you bye.
Thank you very much, Sylvia. So I think we have time for questions. There.
Okay. Thank you very much for the next one. In the context of this Monte Carlo and other things, well, you mentioned the temperature and the capacity and similar things. How do you, let's see, implement temperature in these simulations? I mean, Monte Carlo.
It's classical Monte Carlo. So classical spin. So I have my Hamiltonian, and then I have my spin lattice. I do, I don't know, I can. So it depends, of course, the size of the lattice depends on the spin pressure you have, and then you randomly move. So it's standard Monte Carlo with a classical spin, not quantum Monte Carlo. And so then you make some move, and then you make your average internalization, and then you start evaluating statistically the properties. So
thanks for the talk. Really interesting. So at the beginning of the talk, you clearly stated that you're not working with U parameters through linear response. But I couldn't tell whether to take this opportunity and as all of the DFT+U experts are here as well.
Yeah.
To sort of raise the question that so I understand I never did this before, but when you sort of are fitting your J parameters in your Hamiltonians, what you have to do in DFT is to probe different magnetic states, right? So as you're calculating different magnetic states, you're changing the occupation matrix, right? Essentially. So what would happen if you wanted to be consistent and calculate everything through linear response? My question is, as you change
yeah, no, I understand. I mean, there are systems that are ferromagnetic and they are metallic, and then they go anti-ferromagnetic and they're insulating, and the U would be different, and I don't think you can ever be consistent.
But my question is, okay, U is not an energy constant. So in principle, you're changing your Hamiltonian, and you should never compare total energy. But if you use this prescription to export this part of the linearity, it's dependent on this approach. Would it sort of like use to calculate different values of U, and would it work, or would it make no sense?
Yeah, I don't know. It's a hard. I think it boils down also to the Heisenberg, right? To the Heisenberg approximation that you're doing, right? Heisenberg, you're assuming from the beginning that your spin doesn't change, right? If I rotate it, it's fixed, right? But this is not true if you have a metal, right? So if I have something which is metallic in the ferromagnetic state, then I would say the Heisenberg principle breaks down. So yeah, I mean, if you're strict on that, then I think you cannot evaluate any J principle, right? Whether, this approximation is not rigorously true, but in practice, when you're spin, you're still localized. and you can still, use it, although not rigorously. Maybe that's also true, depending on the system. I mean, of course, I mean, if you do like this oxide, yours be like 5-bond magnet, your spin is localized, and it goes metallic, but then your screening is strong, your interaction are still short range. So I would say that although not rigorously, you can still use it. But whether rigorously you can say that, I don't know, you can evaluate you consistently, this probably is not true.
Yes, first of all, I want to connect to the previous question. I guess it depends on the system based on the experience and on the system and what you saw. What is that depends also on how many J's you include in your model, whether or not the system can be understood as item like or less item. Item means that the spin doesn't change, then the same Hamiltonian can capture from ferromagnetic to the same J. Whether you can do this or not depends on how many J's you in the model. At least.
Yeah, sure. That is true.
And that connects to my first question, which is how do we understand microscopically the second and third level for J's? Because I mean,
Here.
first, you mentioned.
Okay.
I understand that you make a fit, you need those, but then.
Right. I mean, you need in terms of model. Okay, so you can do that. So, well, microscopically, I would say that without resorting to a model, I would say that you get J3, which is large in nickel iodide, just because 5p are broader than 3p, right? So in chloride, your interaction is much short range, right? So basically chloride is more localized, let's say, and if they are third neighbor, they basically don't see each other, but with 5p in iodide, they do see. So this is the first, let's say, microscopic argument that I can make. When J2 is small, okay, so it's probably, then you probably need a model to see which are the orbitals, which we didn't actually do. But we thought that maybe because of let's say in J3, you have, let's say, bridge. So it's kind of super exchange. So I think this you can, we didn't do that, but I guess you can interpret it in terms of super exchange, super exchange. In J2, there's no bridge, basically. So it probably, if you look at the orbitals, which are the most relevant, the shape of this EG, then you would probably see that there's no real connection, the orbital with the overlap with the anion P is probably small. I don't know. But I would say, you can be the model, but we didn't do that.
Yes. So no, my question, I'm sure you relates to this. So, so what is so let's say we are talking about short range interactions, but the point is how short range is it?
Okay, so J4 and J5 is basically Z. So you make a ratio between J4 and J1, and if you get, let's say, minus less than 95%, then your Curie temperature wouldn't change. And this is what I mean by short range. That actually my Curie temperature doesn't change whether I include, longer nearest neighbor.
4 and 5, you mean the distance between the first site and the fourth site.
Fourth nearest neighbor, fifth nearest neighbor might not necessarily be alone.
I see. No, because my point is do you know if there are DMFT, dynamical field theory attempts to tackle, instead of using quantum Monte Carlo, the solutions of the Heisenberg model? Do you know if there are dynamical field theory attempts or not?
For this system, you mean? For in general.
Model, let's say, and then because it would solve, let's say, the problem of which U to use, because any U that you use is the Hubbard model in which you map everything into
Mhm.
spins should be the correct one if let's say the Green's function is the correct one.
Right.
So you understand. So but the problem is that we need to solve the model via dynamic metric theory because yeah.
They can they solve, I mean, can they evaluate the J with single site DMFT? I don't
No.
think so, right? So you have to go beyond like, yeah, two side or, but you need a cluster, right? To get the J. And if you have like 5 or 3rd nearest neighbor, can you do that with DMFT? Isn't it very expensive? I believe it's possible, right? But the computational cost of evaluating from DMFT, the 3rd nearest neighbor, you should do at least 2 octahedron plus, I don't know, something.
Yeah.
It probably goes beyond the current capability. It can be done. I think I'm not an expert on DMFT, but it can be done, right? I don't see why it shouldn't, right? But just it's probably too expensive.
Yeah, I understand.
Yeah, when you say that you're using a standard multi-card. I'm curious if you encounter some kind of computational challenges in terms of the current implementation of this type of system.
Oh, what do you mean?
I don't know. Sometimes
Right. So you mean if you go to low temperature? Hmm?
What the system size?
Yes. Okay. So well, here the skirmion are very small. So as you very small, it's like, I don't know, the cell, the periodicity of the cell is like 8 times 8 lattice constant. So you don't need like very large lattice, even in Monte Carlo. But of course, if you tackle larger skirmions, as you have, right? I mean, some of them are not like, few units, some of them are 100. Then of course you might, the properties that you evaluate actually depend strongly on the lattice. So we always usually converge, the spin texture as a function of the lattice in Monte Carlo. Otherwise, we can never be sure. And I saw many cases in which, for example, if you have a big object, this develops only if it has enough space to develop. Otherwise, you don't get it under the skirmion or anti-skirmion. So in this sense, you don't encounter, I would say, convergence problem, but you encounter problems in results, right? In interpreting the results. So we usually converge it with size. That is we always do.
Could you please go 2 slides back? Yeah.
Yeah.
So actually, yeah, U = 5, J = 1. There are 2 different versions, and
Yes.
completely different and completely different from the other results.
Yes. So this is not my paper, but this is Nicola's paper. But I think this was just to show the equation 6. So okay. So this basically the difference between, let's say, this one and this one is, let's say, the difference between Dudarev and Liechtenstein, let's say. And so you see that they should be equivalent if you have a collinear system, but it's not if you have a non-collinear system. This one, what did they do? They fixed the J to 0 in equation 6. I believe they only they killed this term in the off-diagonal term, and they left it in the diagonal term. And so this again, basically, I guess the message is to show that your J in the off-diagonal term matters. That's their point. Which I mean, it's okay. I mean, it's 5 degrees versus 2 degrees versus 8 degrees. So it's kind of, again, tiny quantities, and micro. So we're in this small delicate regime. But let's say what they show, if you want to evaluate the predicted spin damping angle, then you need to be very careful about it. That's the bottom line. I guess this is what they want to say.
By the way, these energy differences are, the energies are computed as energy differences, different spin structure, do I understand correctly?
Spin direction here. Spin direction. So here it's always C type, but they do like this.
Looks to me a recipe for disaster to compute such small differences.
Sure. Yeah, this is also one of the take-home messages that here we're tackling small energy differences. So if it's micro EV or 100 of micro EV, so in general, it's especially for oxide, it can be problematic. But I mean, magnetic anisotropy for iron can be well estimated by DFT. Is not. I mean, there are many cases in which you can rely on the small energy differences, right? The problem is that when you are complex or correlated or system, that can be hard.
Just a quick follow-up for myself on this.
Mhm.
When, according to your experience, in order to get this different magnetic configuration or sort of magnetic spin orientation, those are with a stable state. You just rely on that, or you have to impose constraints?
Yeah, so you usually add your local magnetic field. There's a penalty function that makes your spin not to deviate from the one you want. So you want the spin to align, I don't know, 5 degrees away from the z-axis, and so you put a penalty function, a Lagrange parameter, and so the spin would, I mean, as you go on with self-consistency, they will align like this. And then of course you have to check. Then of course you have to check in the end that your spins really are as you wanted them to be. Sometimes you try to impose, and then I don't know, this constraining field is not large enough, they deviate, and of course it's micro EV, so your results are wrong. Yeah, so it never converges. So my experience is, especially if you have a complex magnetic configuration, in principle, you let your spin go and they should go to the ground state. In practice, it is never like this, right? So you basically need to have some hint on what your spin configuration might be, and calculate that, and then check the total energy. I generally use VASP. This is where I come from, but I think I don't expect any differences with other codes. I just use VASP because I started with VASP. But I think it can be done, right? I don't know if the J is spin orbit can be non-collinear, and spin orbit with J can be done with quantum espresso, but I don't know.
It can be done, it's not easy. It's not easy, but can be done.
Okay.
Especially non-collinear spin. They tend to go wherever they want and not to.
This also with VASP. They tend to go.
Okay, so I don't see any other raised hands, so in case, let's thank again Silvia.